Right, let's go to the calendar. So calendar hasn't changed since last time. I made those changes with the assignment due today is now due on Monday evening, Precalculus Technology Project number 2, and weekly homework 5, and then this online homework are also due next week. This is just for the corrections, those who are doing the corrections. If you've done them already, I apologize, I have not had a chance to take, excuse me, take a look at them. But our quiz number 2 here next Friday, chapter 3. So chapter 3 is a pretty long chapter. Pretty much broken it up in 2 parts. So the first part talks about polynomial functions. So complex numbers as solutions to mostly quadratic equations, but polynomial equations in general. And then the rational functions, which we're going to do today. And then there's a little bit more about inverses. For those who did technology project number 1, you're kind of getting that same idea. If you have a parabola like this, and you say, is this parabola 1-to-1? It's not. But if you take away half of the parabola, it is a 1-to-1 function. It will pass that horizontal line test. So it is possible in some cases to make restrictions on the domain of your function so that your function will have an inverse. So we're going to do the same thing with trigonometric functions. So there's a little section kind of reviewing the whole concept of inverses. And that's the last part of chapter 3, along with the inequalities. So nothing due today. Hopefully we get all, so far we get in chapter 3. Might not get the 3-8. We'll see how it goes. But I did get your homework completed. So if you go to the gradebook, if you turned it in online, you can just click on the score and it'll take you to the place where your file is uploaded. If you turned it in the old-fashioned way, I do have them. So your score is there. I'll give them to you in class on Monday. So I was going to try to upload those for you, but I didn't get a chance to do that. I'll definitely have those for you in class on Monday. So a reminder, if you're doing a rewrite on technology project, upload it to the same place. I have extended the due dates for those who did it to a week from today. You know, it's not really a hard and fast due date. It's just, don't want you to forget about it. The quicker you can do it, the better. You'll move on to the next one. That's one thing I'm trying to work on, is a better system for the rewrites. But you do have a place to put them. If you can at least tell me if you've done it, I'll take a look probably over the weekend. All right, so you're on online homework number 5 now, starting sections 3.5 through 3.8. That's the one that's due on Monday. The other thing I want to tell you about is once quizzes are completed, everything graded, everybody's taking the quiz. If you go to the place the quiz was over, in this case it was the chapter 1 and chapter 2 quiz, I have uploaded not just a copy of the quiz, but also a key to the quiz. So it has all the answers. So if you just click on this file, it's the quiz itself, a blank version of the quiz. If you click on this file, it'll take you to the key. So we talked about some of the problems in class, but this is a complete key. So you can use that to help you get ready for the midterm exam. I'll continue to do that for the other quizzes. And you can see also there's our 2 lectures from previous Friday. I know we were in person last Friday. I was hoping to do it this week, but we are doing this again. So if you can look under course content, just since we're there, this is everything we're doing in algebra. So chapter 1 through 4 are the basic functions. 9 and 11 are different topics that are important when you get to calculus. Solving systems and equations, always important. Sequences and series, there is a connection between these and functions. You do a whole lot of sequences and series in the second semester of calculus, but we can definitely see a connection right now. So these are all the algebra topics under course content. So let me know if you have any questions about the grade book, about the calendar. It should all be pretty clear. Hoping no more changes in the calendar, so we will have to see. Let's see. So any questions about any of that before we get going here? So I hope you got the message in time, that you didn't show up to class and saw the note on the door saying, hey, we're online today. I was trying to send it out as quickly as possible last night, but might not have been quick enough for some people. But I'd like to start with today is going over questions on the weekly homework. Mostly, it's not that you did it incorrectly necessarily, but the way in which you maybe write some answers. So I want to make sure you understand entering the question correctly and what you need to do on some of these to answer the question. So let's start with this is section 3.2. Let's look at number 10. It's just a quadratic function. So the function was 2x squared plus 8x minus 2. And they wanted the vertex of the parabola. Now you can assume, based on the equation, second degree polynomial equation, graph will be a parabola. And all they wanted here was the vertex. It didn't say how to find the vertex. So we have three ways to find a vertex. You can find the x coordinate by using the negative b over 2a formula. You can graph it and just identify the vertex on the graph, or you could put it in standard form. That means you have to find your h and your k in standard form. Now, most of you decided not to do it this way, which is probably a good idea. If you graph it, all you have to do is identify the maximum or the minimum value. Most of you, I think, use the negative b over 2a formula, which is perfectly fine here. So for the x coordinate, it's negative 8 divided by 2 times 2. So the x coordinate is going to be negative 2. When you're finding the y coordinate, you're putting negative 2 into the function and simplifying. Now, what you can actually do here, and some students do it, let me give you the answer here first. This is 8 minus 16, which is negative 8. Negative 8 minus 10 is negative 18. So the answer to the question is vertex is negative 2, negative 18. And that's all you had to do for this problem. But if you were asked to put this in standard form requires knowing where the vertex is, and that stretch or shrink factor vertically. This number is your stretch or shrink factor vertically. So if you wanted it in standard form, you could use what you know about the vertex location and say, here it is. So there's your standard form. So if you're asked to put one of these quadratic functions in standard form, this is a way to do it. So I want to point out, all you had to do for this problem was identify the vertex. And as I said, most of you use the negative b over 2a formula, perfectly fine. I like looking at graphs, but as you know, some of the applications, graphing might take a little bit of adjustment in the window size, so it might take you a little longer. This is probably a quicker way to get the answer. All right, let's do 3.3 number 54, next one. This is a function already in factored form, and you had to answer some questions about this function. So this was the polynomial. Now I want to point out that when you are trying to graph these, end behavior, X intercepts, all the information we're trying to find out about these functions, it's very helpful to have them in factored form. You'll know right away where the X intercepts are. You'll know right away what the multiplicities are for the zeros. You can get the Y intercept very quickly. And the only thing you really can't get quickly, I think, is the end behavior. But if you look at the X's here, X times negative 2x times negative 2x squared, that should tell you what your end behavior is without even graphing it. This one is asking for the X intercepts and the end behavior. So I pointed this out in class. I want to make sure you understand the difference between the two. Factored form will give you the X intercepts. It will give you the zeros. What's the difference between the zeros and the X intercepts? That is a 0. That is a 0. And that is a 0. Because zeros are the numbers that make the equation true. F of x is equal to 0. So maybe not the best terminology, as I was saying, but these are zeros. If you want the x-intercepts are points. So you should take it one step further and write these as ordered pairs. So 0, 0, 7, 0, 5, 0. That's all you have to do for that. So if you're graphing it, you identify those points. So 0, 0, 5, 0, and 7, 0. Now we're going to do this without the calculator. End behavior. If you were to multiply it out, don't have to, x times negative 2x is negative 2x squared. Negative 2x times negative 2x is 4x squared. So if you multiply everything out, you're going to have x times x times x squared, x to the fourth, is the leading coefficient positive or negative? It would be negative. And that means Naruto, both sides down. This, when you talk about the zeros, this has one X intercept at 5, 0. But it has a 0 of multiplicity 2 that is a repeated factor. Makes a difference when you're drawing the graph. So if the end behavior is down, you go down from 0, 0 to the left. And it's got to go up and then come back down and intersect the x-axis for sure at 5, 0. But what does it do at 5, 0? Does it do that or does it stay on the same side? Since the multiplicity is 2, it's going to stay on the same side. So it goes up like that. And that's got to go up, come back down, go through the last x-intercept, making sure the multiplicity is 1, which it is. And there's a very quick sketch for the graph. So I don't know if it asked for a graph on that one. It definitely asked for the x-intercepts at the end here. So if you have a polynomial that has all terms, x cubed, x squared, et cetera, and you factor it. Factored form helps us with the x-intercepts. It helps us with the zeros. Doesn't necessarily help us with the end behavior, but we can get the end behavior from the factored form. If you have all the terms being added and subtracted and set equal to 0, not gonna be able to solve that. So that's why we like factored form. All right, then a couple in 3, 4. Let's do number 34 first. So 34 has this function. It was a 2x plus 1 cubed, and then 9x squared, minus 6x plus 1. And you're asked to find the zeros and their multiplicities. So it's not asking for x-intercepts here. It's asking for the zeros. But if you know where the x-intercepts are, you know what the zeros are. This factor is there 3 times. So if you set 2x plus 1 equal to 0, you'll find that first 0. And the first 0 is negative 1/2. But how many negative 1/2 are there when we count them? There are 3. So this one has a multiplicity of 3. This is not factored, but if you factor it further, you'll be able to tell where the other zeros are going to be. And maybe you recognize this as a perfect square trinomial. If you didn't, when you go to try to factor it, you try 3x and x. There's only one way to get a 1 here and a negative 6 in the middle, and that's having both of these be negative 1. And you can see that it's actually going to work. Negative 1 times 3 is negative 3. 3 times negative 1 is negative 3. There's your negative 6. But because it's a perfect square trinomial, you can write it this way. Oops, I lost the 2 there. So 1/3 is a 0, but how many are there? There are 2 of them. So this is a 5th degree polynomial, but only has 2 unique zeros, both with multiplicities. So one with multiplicity 3, one with multiplicity 2. Those 2 together give you the degree of the polynomial. So if I were to ask you, does this function have any complex zeros? I should say non-real complex zeros. It doesn't. It's a 5th degree polynomial. Even though only 2 unique answers, it has 5 total when you count the multiplicities. There are no complex, non-real complex ones to worry about, which is good. Those are, as you saw in class, a pain to deal with.
I did have a quick question on that. Oh, sorry.
Go ahead, Bailey.
So for number 34, like in the quiz or test scenario, I know that you could either set, in the factored form, you could set them both equal to 0 and find the zeros that way. But say, are we just as able to put it in our graph and find them graphically
Yes.
as well? Is that acceptable?
You can,
Okay, good.
yes. I've been encouraging you to look at graphs on these. So graphing or algebra would work well here. Right. And number 60 is one of those questions where you're asked to come up with an equation for your polynomial. So if I give you a picture like this, you should be able to come up with an equation. If you're given a description of the polynomial, you should be able to come up with an equation. This was a description. So you're supposed to find a polynomial function. Let's see, I think it was degree 4 with these characteristics. It has a 0 at x equal 4 with a multiplicity of 2. It has a 0 at x equal 1 and negative 2. Those both have multiplicities 1. And it passes through 0, negative 3. So if you have some information about the X intercepts or the zeros, multiplicities, you can turn those into factors. If you know one other point that's on the graph, you can use that to find the stretching or shrinking factor. So the way you want to start this problem is take each statement about the zeros, multiplicity 2, turn this into a factor. X equal 4 is your 0, x minus 4 is your factor. Multiplicity 2 means you're going to have 2 factors. So write it as x minus 4 squared. X minus 1, turn that into a factor. X equal negative 2, turn that into a factor. That's your 4 factors that you need. So when you start writing your polynomial, put the a out front. We have to determine a after the other factors have been determined, and write the product of your factors. Okay, so any 4th degree polynomial that has zeros at 4, 1, and negative 2, with a multiplicity of 2 at 4, looks like this. Now, there are many polynomials that look like this. If a is a negative number, for example, your graph would have been flipped. A is a number bigger than 1, a is a number less than 1. So the graph would be stretched out or shrunk. What doesn't change, though, are the x-intercepts. No matter what a is, if x is equal to 4, you're multiplying everything by 0. So that's the nice thing about doing it this way, is if you have this extra point here that you know is on the graph, that helps you determine a. So use this point to help you figure out a. So that means when x is 0, 0 in for x, y is equal to negative 3. And the only thing left to find is a. So solve the equation for a. This is negative 4 squared, so that's positive 16. This is negative 1, and this is positive 2. So it's negative 3 is equal to a times negative 32. So quite a interesting shrink factor there. It's 3 over 32. So graph's really been compressed in this direction, but that's how you find it. So that is a definite standard question that you need to know how to do with any type of function. How do we find the equation for a linear function? How do we find the equation for a quadratic function? How do we find the equation for a polynomial function of a certain degree? We'll ask the same question for rational functions. All right, here's your chance to do a screenshot if you want. Because I'm going to get rid of this, and we'll go to the in-class sheet we were working on last time. So any questions about that? Anything? Okay. So like I said, most of the homework was perfectly fine. I think you did a pretty good job on it. Just wanted to point out a couple of things about the vocabulary in this section. So talking about zeros versus x-intercepts. When you're sketching a graph, how much detail do you need to show? How do you find the vertex of a of a parabola. So questions like that. All right, so let's go to where we were at the end of class on Wednesday. So we're talking about section 3.7. In our book, section 3.7 is the section on rational functions. So this is really your long-winded definition. If you like your subscripts, there it is. But the basic definition is it's quotient. That's polynomial. That's polynomial. So that's what makes a function a rational function. Now, just a word of note here. There was a question on the quiz that looked like this. I don't remember the exact polynomial in the denominator. But is that a rational function? No. Square root of x minus 3 is not a polynomial. So this is what we call a algebraic function. It's not a rational function. You can still get the domain and things like that, but we're not going to consider this in the category of rational functions because this has some different characteristics than a rational function has. So this is an example of one that's not rational because of the square root. If that was x plus x minus 3 in the denominator, we're fine. Okay. So think about x minus 3 under the radical, x to the 2/3 power, things like that. Those are not going to be examples of rational functions. So lots of domains of our rational functions are restricted because you cannot divide by 0. So if you look at number 1, find the domain. You need to make sure that x squared minus 2x minus 8 is not going to be 0. They, I think, intentionally gave you this as something you could factor. You could also use the quadratic formula. Two numbers multiplying to -8, adding to -2. Once you write those down, you say, if I try to use 4 as my input, or I try to use -2 as my input, neither of those numbers will work because you're dividing by 0. So something to definitely remember here. If I put 4 in for x, the denominator is 0. If I put -2 in for x, the denominator is 0. But if you put 2 in for x, your numerator is 0, your denominator is 4 minus 4 minus 8, it'd be -8. What is 0 divided by -8? 0. That is an X intercept. But f of -2 has us with a 0 in the denominator, and this is undivided. So difference between 0 over a number, which is not 0, versus a number divided by 0. This, your calculator, of course, cannot do. This, your calculator should give you an answer of 0, hopefully. If it doesn't, I think you should get a new calculator. But this is the same question we asked before when you're finding domains. One of the problem spots to watch out for, division by an expression. So if that expression is equal to 0, can't use it. So rational functions, watch out for the domains. Anything under a radical that is a power of 2 or 4. We'll be adding one in the next chapter with logarithms. Logarithms also have restricted domains. So I think I asked you for this before, I'll just kind of add it in here. This function right here, even though it's not a rational function, if I asked you for the domain in this function, x can't be 3, that would make this 0. But we also have the added restriction that x minus 3 under the radical, x minus 3 needs to be non-negative. So the actual domain here is not equal to 3, but numbers bigger than 3. Otherwise, you wouldn't be able to evaluate this expression. All right, so we talked about this idea of an asymptote. 1 over x has 2 asymptotes, one vertical, one horizontal. So before we do a little bit more general discussion about this, let's take 1 over x and move it 3 units to the right and up 2 units. So thinking in terms of our transformations. We know that the horizontal asymptote, I abbreviate HA, is the x-axis. We know the vertical asymptote, abbreviated VA, is the y-axis. What do you think the horizontal and vertical asymptotes will be for the transformed graph? So we think about 1 over x, looks like this. You're going to move the graph 3 units to the right. Is that going to affect the horizontal asymptote? Is it going to affect the vertical asymptote? It's going to affect the vertical asymptote. And that's because you're moving it 3 units to the right. So your new graph is going to look like this. So a new vertical asymptote. So this one will have a vertical asymptote of x equal 3. Still the same horizontal. It'll approach at different rates than the first one, but it'll still get closer and closer to the x-axis there. So same horizontal. But now do the second step. Move the whole graph up 2. So if the graph gets moved up 2, see if you can make a prediction here. Same vertical asymptote, but now we have a new horizontal. Any predictions on the new horizontal? It was at 0. We moved everything up 2 units. Why not 2? Why not 2? And you can kind of visualize it here. This would be the vertical and horizontals on the last graph. So when you do your 2-step transformation, right 3, up 2. Vertical changes in the first one, horizontal changes in the second one. Because the question is going to be, is it possible to take a look at the equation of our rational function and predict where these asymptotes are? If we're going to graph the function, that's another feature we're going to need to include on the graph. Because X intercepts for the polynomials and behavior, we use that information. Here we also need to use information about the asymptote. So word of warning though, when you go to the calculator or Desmos and try to graph this, when you type in the function, make sure the denominator is in parentheses. Because if you type this in as 1 over x minus 3, no parentheses, it's going to do 1 over x first and then do minus 3. That's a different transformation. That one will go down 3, not to the right 3. So very careful with your parentheses there. And then plus 2 afterwards. So we got the standard window here. I think I had shrunk it before to show you in class what the reciprocal function looked like in a narrower window. Let's go back to the standard here. Okay, so you saw the graph that I drew, right 3, up 2. This is what it looks like. Now, just a quick word about these calculators. Things are getting better. When we first did these types of problems on a calculator, the first versions of the graphing calculator, would you believe, actually drew in this line. And that was really confusing for the students because they thought, oh, wait a minute, it looks like a vertical line. Can't be a function, right? That's just the way the calculator was programmed. It was playing connect the dots. It takes a few of these points and then plays connect the dots. And then the problem is this graph drops off the table here, but then there's a separate part of the graph that starts up here and goes down. The only way the old calculators knew how to do it was to make it look like those two are connected. Okay, so fortunately that doesn't happen anymore. It's less confusing, I think, for the students. Now, can you see the vertical asymptote here? Can you see it as that actually x equal 3? You should be able to see that. What's a little bit harder to see is kind of where this horizontal is. We know it's at 2 from what we calculated before. This is 0, 2 right here. If you were to kind of trace along the graph here, you can kind of make a prediction and say, okay, as we go to the left, the numbers seem to be getting bigger. Even when we get to the end of our screen here, it's only up to 1.92. We said that the horizontal asymptote was 2. Sometimes it takes a real long time for the function to start approaching that horizontal asymptote. So when we make that statement, as x gets smaller, going to negative infinity, function approaches 2. It's not saying how fast it's approaching 2. It's also not saying what direction it's approaching to, above or below. So you have to be a little bit more careful when you're trying to graph it. It's nice to know where the asymptote is, but you also need to know how the function is approaching the asymptote. So horizontals, below or above, verticals going up, going down. So this one you can say, yeah, it's getting closer to 2. It's going to take a while, but it's going to get out to numbers that are very close to 2. So when you draw these by hand, I would appreciate dotted lines for the asymptotes, because we're actually can draw these a little better than the calculator can, because we can put in those dotted lines. So if I ask you to draw this function kind of on its own, go out to 3, draw your vertical dotted line, and say that is your vertical asymptote. And remember, asymptotes are lines. So when you draw it, it's a vertical line. Make it dotted because it's not actually part of the graph. But it's a line, so make sure to write its equation. Don't just say vertical asymptote 3. It's x equal 3. Same thing is true for the horizontal. Don't just say 2, say y is equal to 2. Okay, so we have those 2 parts of the graph already figured out. We then draw the rest of it so it looks like this. So if you know how the function is approaching the asymptotes, you really don't need any other points here. But you can figure out, it looks like we do have an x-intercept and a y-intercept here. You should be able to get the y-intercept, no issues. Put 0 in for x and solve for, evaluate the function. So it's 2 minus 1/3, which should be 5/3. So this point is 0, 5/3. The x-intercept, you'd have to solve a rational expression equation. You should know how to do those, but it's actually solving an equation. So I'll take you a little bit more to do that. But 1 minus over x minus 3 plus 2 is equal to 0. So this is how we're going to proceed in terms of graphing these rational functions. Find the domain, identify the asymptotes, vertical, horizontal, intercepts, x, y intercepts, and hopefully that information will be enough to sketch the graph. We're trying to get away from point plotting. In the old days, we try to find like 5 or 6 points that are on the graph, and then they're all over the place. It's like, oh, well, this part looks like this, and this part looks like this. Now, it's a little bit more streamlined process. We know where these asymptotes are. We're just using a few key points on the graph to make us sketch what the rest of the graph looks like. So if we know where these asymptotes are and the intercepts, we can get a pretty good sketch of the graph pretty quickly here. So let's go ahead and do number 2. It says find the domain. If we look at the denominator, we need to see whether the denominator can be 0 or not. So what do you think? 2x squared and plus 11x minus 12 equal to 0. If this is factorable, 2x and x. So we need 2 numbers multiplying to 12 and adding to 11. What do you think? 2 numbers multiplying to 12, adding to 11? 12 and 1? Nope. 6 and 2? Nope. How about 4 and 3? So since this is number 0, this function actually has no restrictions in its domain. So not possible to factor. So what that means is you can just say you're never going to be dividing by 0, so you can write down domain and solve values x. Anybody want to make a prediction as to where the horizontal asymptote will be here? If there is no restriction in the domain, the graph will not have one of these vertical asymptotes. Simple as that. So that's what's kind of different about these rational functions. These asymptotes are out there. A lot of these functions have them, but they don't always have to have them. You can have a rational function that has neither. It all depends on what the relationship is between the numerator and denominator. So this one has both. This one does not have a vertical asymptote because there are no restrictions in the domain. It does have a horizontal asymptote. Anybody want to make a prediction here? The hint I will give you is look at where the highest power of x is. Is it in the numerator? Is it in the denominator? This one's in the denominator. So one way to consider it is Horizontal asymptotes come into play as x gets bigger or as x gets smaller. If I take a number that's really, really big, x squared is going to get bigger at a faster rate than x. Another way of saying that is if I were to take x over x and 2x squared over x, this would look like 1. This would look like 2x. So what that means is as x gets bigger, the number in the denominator is getting bigger at a faster rate than the numerator. So it's kind of like 1 over x. So 1 over x, what happens as x gets bigger? Outputs approach 0. So one generalization we're going to make, and it's kind of explained down here. Check out the degrees of the numerator and the denominator. Just compare them. If the degree in the denominator is larger, so the degree of the denominator is larger than the degree of the numerator, you automatically have that being your horizontal asymptote, y equals 0. It just means that the denominator is getting closer to 0 at a faster rate than the numerator is. So that's one possibility. The second possibility is to have a graph like this. So here's a rational function, 2x cubed minus 1 over x. Where is the highest power of x in this function? Upstairs, numerator. That is the second case. Degree of the numerator is greater than the degree of the denominator. I'm going to cross these off for the moment. We're not going to talk about these yet. If this degree is larger than this degree, no horizontal asymptote. So kind of think about the opposite of this situation right here. If you took everything and divided by x, your numerator would be 2x squared. Your denominator would be 1. So as x got bigger, 2x squared keeps getting bigger and bigger and bigger and bigger. 1 stays at 1. So for this one here, there is no horizontal asymptote. So third case is when they're the same. So when they are the same, I'm going to take this one here and write it in a different form so you can actually see it here. So this is taking 1 over x minus 3 plus 2 and writing it as a single rational expression. Take a look at the numerator and the denominator. Where is the highest power of x? It's the same in both the numerator and denominator. So we try the same technique of dividing by x. 2x over x and x over x both produce constants. One of them is 2 and the other one is 1. So that is going to be your horizontal asymptote. Y equal 2. So those are the three cases, trying to determine where your horizontal asymptotes are going to be. So largest power in the denominator, automatically 0. Largest power in the numerator, no horizontal. Highest power of x the same, do the quotient. So do 2x divided by x, and that tells you what the horizontal asymptote is. So remember, this is long run end term behavior. So even though when you're kind of close to 0, your numbers are kind of fluctuating a little bit, we're saying after a while, they're going to start trending towards this number. So in the beginning, 0 minus 5 over 0 minus 3 doesn't sound like a number very close to 2. But as x gets bigger, it's insignificant. It doesn't matter what you're adding and subtracting. You could add 100 and subtract 1,000, but x keeps getting bigger and bigger and bigger. So ignore the terms that don't involve the variable. Just look at the ones that do have the variable. Right, so the answer to part B is actually up here. Sorry, my work is all over the place. Horizontal asymptote for that function is y equals 0. Okay, and then for the vertical asymptotes, you essentially find the domain of your function. Any place where you have a number that's not in the domain could possibly be a vertical asymptote. So x could not be equal to 3 here, turned into a vertical asymptote. There's one exception to that rule, which we'll get at the end of this section here. And that's number 5. So let's hold off on number 5 right now. So to get the vertical asymptotes, you want to factor both the numerator and denominator if possible. Get the restrictions on the domain. That comes from setting the denominator equal to 0. Those are numbers that are not going to be in the domain. This number 5 is going to occur when we have common factors of the polynomial in both the numerator and denominator. So if we go back to the original rational function we took a look at here, your first step is to write this in factored form. So the denominator is x minus 4 times x plus 2. I thought we were in class. I just pointed to it. Did you see me point to it? It's right there. And x squared minus 4 in the numerator is actually x minus 2 times x plus 2. So if we were to start this problem using those directions, you would still find the domain to be the same. No numbers equal to 4 or negative 2 are in the domain. But this is a common factor. Another way to write this would be x minus 2 over x minus 4. Still the same domain. But when it comes to graphing this function, you will not have a vertical asymptote at x equal negative 2. Now we'll see what happens at that point when we graph it. Okay, so f had no vertical asymptotes since the domain was all x. So I'll make sure we have the right function there. I'm going to make a little switch here. Let's answer these same questions. I'm now looking at these functions that they're working with here. It does say to use f, but I think it would be more beneficial for us to not use this f. I think that should be a different letter. So I'm going to make a little switch here. I'm going to call this h of x. So all these questions we're now answering about domain, range, horizontal, and vertical asymptotes are based on this function right here. So this is what we're going to take a look at. So let me go down where there's actually room to write that and then go from there. Okay, so if f of x is this function, x squared minus 4 divided by x squared minus 2x. That's it. We factor the numerator and denominator. Cancel our common factors, and we're left with x minus 2 over x minus 4. Let's just go ahead and write down the domain. The domain, all x values that are not equal to 4 or negative 2. Vertical asymptotes are going to occur at x equal 4, not at x equal negative 2. We'll talk about that situation in a minute. Your horizontal asymptotes, where is the highest power of x in this rational function? Numerator has x squared, denominator has x squared. It's the same. So take the highest power of x, those two terms in both the numerator and denominator, and take their quotients. So after a while, it's going to look like 1. So we have a horizontal asymptote. I like 1. These two numbers are going to help us. Actually, this number right here will help us with the x-intercept of the graph. So the x-intercept of the graph is going to be at 2, 0. The y-intercept of the graph is going to be at -2/-4, which is 1/2. So we're going to put all this information together to give us our graph. So x = 4 is the vertical asymptote, y = 1 is the horizontal, and we got these 2 points right here. And then we're going to try to figure out what's going on here at -2. Okay, so here it is. So this is the graph of f of x. So we have a horizontal asymptote at y = 1. We have a vertical at x = 4. So put those two in first. We had a y-intercept of 0, 1/2, I believe, which is right there. And we had an x-intercept at 2, 0, which is right here. All right. Now here's the issue. I think you can see based on these 2 points how the function is going to approach the vertical asymptote in this direction and how it's going to approach the horizontal asymptote in this direction. So eventually it's going to start approaching it. This is going to go through the x-intercept and go down. You could reasonably argue here the reason it doesn't go up is because there's only one x-intercept. The graph will not intersect here too and go back up. It'll just continue to go down. That's going to help us with the graph on this part of the function as well, because there are no more x-intercepts. So your 2 possibilities to your graph here are going to look like this, or they're going to look like this. Because we don't know how it approaches that horizontal asymptote. It's just going to approach one eventually. So which one do you think it is? Above or below? Can't be below because there are no more x-intercepts. This is the only x-intercept. So using that to help you with the graph, you can erase this part and say can't happen and just draw this other part. And you don't even need any points to help you draw that. All right, so there it is right there. Last question is, what's going on at x = -2? Okay, f of -2 is undefined. But when this is true, one of 2 things is going to happen. You will get a vertical asymptote at that point. We do not have a vertical asymptote here. You can see the graph is kind of going up, and eventually it's going to start approaching that horizontal line. So what's the other possibility? Let's go to the calculator. I don't know what's going to happen here. It might depend on the size of the screen we use, but going in cold on this one. I'm going to type in the function, the original function, not the factored form. So x squared minus 4 is in the numerator. And then divide by x squared minus 2x minus 8. That's the denominator. Okay. Now you saw most of the graph there. So we saw where the asymptotes were. Look at this calculator graph as you get closer to -2. So it's the blue graph. Let's stick with the standard viewing window. Let's see what happens. Ready? You're excited, aren't you? Maybe not. I am. I'm trying to see what's going to happen here. Okay, it didn't happen. It didn't happen. It looks like you're just going along the graph, and it starts approaching y = 1, which is what we were expecting. And here's that vertical asymptote. Let me try and reduce the window size a little bit here. Once again, I don't know what's going to happen here, so. Just trying a couple things. Okay, so same graph. We're just kind of zooming in a little bit. We're going -3 to 3, 0 to 2. Trying to figure out what's going on here at -2. It worked. See it? There's a hole there. Right there. It decided not to continue the graph. It's a really smart calculator because here's -2. Remember, the function's not defined at -2, but there's no vertical asymptote there. So what's going on at -2? It's a hole. The book defines it as in calculus, we call it a removable discontinuity. We're not doing the actual rigorous definition of continuity in this class, but you can see that in order to finish the graph of this, you can't just continue on in this direction. You actually have to pick up your pen or pencil and restart the graph over here. So when that happens, it's not continuous. So just a quick, probably know this, but we like the continuous functions in calculus. We like them in pre-calculus too, but definitely in calculus. So you're the hole in the graph. You say, well, maybe the calculators didn't know what to do. Of course it doesn't know what to do because at -2, undefined. See that right down there? Doesn't give an answer when x is -2. Now, this only happens in one instance. Look at the original function, x squared minus 4, x squared minus 2x minus 8 are the two polynomials in the numerator and denominator. When they were factored, they had a common factor, and the common factor was x plus 2. That is the only time you're going to get a hole in the graph. Now, when you're drawing these by hand, you need to also include the hole in the graph. So that's why I didn't quite complete the graph before. That's what it looks like. We can even be more precise and say, if this was allowed at -2, we would have a corresponding output. -4 divided by -6 would be 2/3, is a hole in the graph. So I just want to point out, most every single problem like this, not in the domain, will turn into a vertical asymptote. But if both the numerator and denominator are factorable, there is a possibility that you'll get a hole in the graph. So when this happens, when you put your number in as a possible input, you're going to expect to get a hole in the graph. And that just means the numerator and denominator are both 0 at the same time. It's kind of an even more complicated example of something that's undefined, because anything divided by 0 is undefined. But 0 over 0 is really undefined. There's something really different about what's going on there. We investigate this a lot in calculus. We talk about limits. As x gets close to 0, as y gets close to 0, what happens? It turns out a number of things could happen. But when you have a number divided by 0, this is definitely undefined. There's nothing you can do about that. So this is what you get for the vertical asymptotes. What you get for the holes. Okay. I like to do these kind of backwards sometimes. I did the technology to help us figure out where the hole was. So I was kind of putting these together to like not using one to check the other necessarily. But I like my graph better so you can see where the asymptotes are. Except, yeah, the calculator can draw a much smoother graph than I can. So I'll give it that. It does a better job of drawing the graphs. All right, so any other questions about that problem? There's a lot packed into to that one example. It is everything you need to know about these rational functions. So domain, vertical asymptotes, horizontal asymptotes, X intercepts, Y intercepts. This one actually has the hole in the graph. Okay, so just some guidelines when you're trying to sketch these by hand. I've already talked about them. Evaluate the function, find your intercepts, factor your numerators and denominators, get your domain, get your vertical asymptotes. Multiplicities of zeros come into play here as well, because if there's a repeated factor, it's going to look like a parabola at that x-intercept. The only difference here now is we have to include the asymptotes as part of our graph. So let's try another one here. Here's number 3. And we've already got this one in factored form. So we'll find the domain, find the horizontal, find the vertical, find any removable discontinuities if the numerator and denominator are both 0 at the same time, X and Y intercepts, and then we'll get the graph. So first of all, domain. Looks like we are divided by x minus 3, so we need to stay away from 3. Now I'm going to jump down to this question because these questions are related, A and C and D. I would actually reverse the roles here. I would find these two before I found the horizontal, just the way I like to do things. But you can certainly find the horizontal anytime you want. But once you know this answer, you can answer both C and D. So is it true that x equals 3 is going to be a vertical asymptote? Yes. Are there going to be any removable discontinuities? No. And you can just say there's no instance in this rational function that has a situation where we're doing 0, 0. X, Y intercepts, you can once again find those anytime you want. F of 0 is going to be 1 times 5 divided by -3. Now, the factored form is very helpful for us in order to determine the x-intercepts. So the x-intercepts, you're going to still set f of x equal to 0. But remember, when you're solving a rational expression equation that's set equal to 0, it's the numerator that's got to be 0, not the denominator. So for this one, you can say x plus 1 times x minus 5 will be 0. So we have two x-intercepts, -1, 0, and 5, 0. All right, so horizontal asymptote. Where is the highest power of x in this problem? I know we have it in factored form, but if you were to multiply out the numerator, you have two factors involving x, x squared. Only one factor in the denominator, x. So if we did multiply it out, numerator is x squared, denominator is x. If we take those two together, it looks like x. So as, excuse me, as x gets bigger, function values are getting bigger. So no horizontal. So that's the information we need to get our sketch here. Okay, dotted line was x equal 3 was the vertical. I can draw lines much better when I'm given a little template there. So no horizontal, so no horizontal dotted line. We had two x-intercepts of, my memory is shot already. -1, 0, and 5, 0. Okay. And then our y-intercept was 0, -5/3, I believe. Yes, okay. We're about there. Okay, so since there's no horizontal asymptote, we just have to figure out how is the function approaching the vertical asymptote. So I think it's pretty clear this one is going to go down and this one's going to go up. And remember, it's not approaching anything. So you're just getting a really quick sketch here. I would just kind of draw it like this. And don't have it approach anything, just go up. This one, it's really one of two things. It's either going to be approaching it in this direction or in this direction. I suppose you can flip a coin. I suppose you put it on your calculator. Which one seems more likely here? It's actually the top one. And the reason for that is, think about the reciprocal squared function. think about its vertical asymptote, which was the y-axis. And notice both sides of that rational function went up. X minus 3 in the denominator was a single factor. That would indicate here the graph goes up. So get a graph count looks like that. So if it was x minus 3 squared, I would vote for a graph that looks like this. So those repeated factors are going to come into play, not only for the x intercepts, but also for the asymptotes, trying to figure out how the function's approaching the vertical asymptote, above or below for horizontal, going up or going down for the vertical. So this is kind of what the graph looks like. I like it when they say draw a smooth curve. I can draw a smooth curve. I just can't draw very nice looking curves. It should be relatively accurate. So before we do these write the equation type problems, I'm going to do this one on the calculator just because I don't want to spend too much time analyzing it by hand. Because I do want to show you an example of one. First of all, that has two vertical asymptotes and also a repeated 0. So if you look at g of x here, x squared times x plus 3 divided by x plus minus 1 times x plus 2. Your x intercepts are going to be a negative 3, 0 and 0, 0. Your y-intercept is going to be at 3 divided by negative 2. So negative 3 over 2. You're going to have two vertical asymptotes at 1 and negative 2. Will this graph have a horizontal? Where is the highest power of x? If you were to multiply everything out, it's in the numerator. So that means no horizontal. So kind of like this graph right here. So let's go to the calculator and see what the graph looks like if you were to plot these points and knowing where those vertical asymptotes are. Okay, I'm going to keep this and just type in this new one. And we need two sets of parentheses here. So parentheses for the x squared times, I've already forgotten what it was. It was x minus 3. I need a better memory. Plus 3, and then x minus 1, x plus 2. Okay. Okay, so there's the numerator, and here's the denominator. So x minus 1 times x plus 2. Okay, so notice the two extra sets of parentheses indicate numerator and denominator. Let's go back to the standard window here. Okay, so I got the two verticals, one y-intercept, two x-intercepts. Focus on what's happening at x equals 0. It should intersect the x-axis, but stay on the same side, whether it's above or below. So here it is. Oh, I thought I was doing standard, sorry. There we go. So there it is. You can see your behavior here at x equal 0. There's your x equal negative 3. Here's your vertical at x equal negative 2, vertical at x equal 1, and then no horizontal. So the graph just continues on in this direction, continues on in this direction. So we take that into account when we are trying to write an equation for these rational functions. So if there's a repeated factor, multiplicity more than 1, or what happens when your denominator has a repeated factor. Now we know the end behavior or the behavior near the vertical asymptote, up or down. So I'll give you a quick sketch here. So 1, -2, 0, 0, -3, 0, and then 0, -3/2. That was not calculated correctly. Sorry, I was just thinking about this. It should be 0, 0. Because if the y-intercept is, or x-intercept is 0, 0. I did not calculate that one correctly. All right, so remember the graph looked like this. Up on this side, up and then back down, and then kind of down on this side. Actually kind of did this to me, okay. That's more type of a question we'll analyze in calculus. So just focusing on asymptotes, intercepts, how does the function intersect at the intersect at the intercepts, and how does it approach the asymptotes? So going up or going down, or for horizontal, approaching it from above or below. So there should be enough information in the problem to help you determine that without having to plot any points. So let's try to put this all together and come up with an equation here for this rational function. So we need to take what we know about vertical asymptotes, x-intercepts for sure. It'd be nice to know where the horizontal asymptote is. That might be helpful. But for this one here, you can definitely see x-intercept here, 2, 0. Vertical asymptote x equal 4. Vertical asymptote at x equal -1. And I'm just going to put this in. Our function in the end should have a horizontal asymptote y equals 0. Now, if you kind of work backwards here, what does that mean? It means as x gets bigger, your output should get closer to 0. When we were determining horizontal asymptotes before, that's the situation where the highest power of x was in the denominator instead of the numerator. So what's going on here at 2? Does that look like it might be a repeated x-intercept? No. So x minus 2 is going to be a factor in this rational function. X equal -1. Notice the behavior of the function near x equal -1. One side up, other side down. So we're going to need a factor of x plus 1. This one, on the other hand, is x equal 4. Both sides are going down, not the opposite like you see here and here. That indicates a repeated factor in the denominator. So here's what we have so far. This is just information based on the intercepts and the vertical asymptotes. So we have x minus 2, that comes from that point right there. We have x plus 1 in the denominator, comes from the vertical asymptote. We have x minus 4, also a vertical asymptote. But notice, both sides are going down. It would also be the same if both sides are going up. Repeated factor. So it's kind of like the multiplicity 2 for one of these, 0. So staying on the same side, approaching -infinity instead of being opposite. And then we do these the same way we did the polynomials. Determine A. And that's, think about it as a vertical stretch or shrink factor. All we need to do there is use one other point on the graph. Hopefully, you can determine pretty quickly what the y-intercept is. So we're going to use 0, 1 to find A. So this, to me, you can do this. You're working backwards from the graph, coming up with the equation. You're more than 75% of the way there. Because determining A means you have to find A based on another point on the graph. But You're not getting it without these factors. So not just the factors, but also the powers on their factors. And new twist here, numerator or denominator. So denominators have to do with vertical asymptotes. Numerators have to do with X intercepts. Okay, so we'll put a 0 in for X. 1 in for Y, and we will find what A is equal to. So it's really hard when you're looking at these. I couldn't even tell you whether A was positive or negative to look at this, because these graphs aren't really good descriptions of like a translated 1 over X, for example. I would just go ahead and calculate it and trust your calculation. So what do you know? A is negative. A is equal to negative 8. So one last thing you want to check here when you write down your equation. You don't have to multiply everything out. You can just leave it. Make sure, even though we didn't really use this when we're calculating the equation, make sure your y-intercept is what it should be. Is your y-intercept, not y-intercept, horizontal asymptote. Is your horizontal asymptote still y equals 0? Where is the highest power of X in that equation? If you say it's in the denominator, thumbs up. So there's your equation. Okay, I'm not going to verify this on technology. I feel pretty confident. All that would mean is you type in your equation, what pops up on the screen better look like what you see on the screen right now. Like I said, I'm feeling pretty confident about this one. So you could graph it if you want to, but I like it. Okay. So any other questions about that one? On Wednesday, we talked a little bit about inequalities. You could also do inequalities with rational functions. And I once again emphasize, use your graph. In fact, if I gave you this graph and I said, let's call this f of x, knowing what the graph looks like, where is f of x equal to 0? One place, x equal to. Where is f of x going to be less than or greater than 0? Which intervals would, let's do the first one. Where is the graph above the x-axis? Where is the graph below the x-axis? So above the x-axis, let's use a color you can actually see here, green. This part of the graph is above the x-axis. Which part or parts of the graph will be below the x-axis? Here, here, and also here. Now remember, the asymptote is y equals 0. So it looks like we might have an x-intercept coming up here. Nope, graph stays below the x-axis. So pink part of the graph is below the x-axis. Green part of the graph is above the x-axis. All you need now is to determine which intervals you're talking about here. So start all the way to the left. If we stay to the left of -1, graph is below the x-axis. Sorry, wrong color. So I just write x is less than -1. We get change at -1. One side was going down, the other side's going up. So from -1 to 2, the graph is above the x-axis. 2, it's equal to 0. From 2 to 4, the graph is below the x-axis again. Now, here's the difference with some of these rational functions. You could get a change in the algebraic sign at an x-intercept, or you could also have it at a vertical asymptote. So notice we get a change here. One side is negative, one side is positive. Here, we do not get a change. Both sides are negative. So that means once you get to 4, anything bigger than 4 will also be negative. No change there. No change. So when you are doing these types of inequalities, if you have a graph, use the graph. If you don't have a graph, get a graph. You don't even need a real detailed graph. You just need to know where are the x-intercepts Where are the vertical asymptotes? And is the function doing this or this at a vertical asymptote? Is the function doing this or this at an x-intercept? So it's like an extra step because you could have these vertical asymptotes involved, but we do these kind of at the same time we do polynomial functions with the inequalities, because to me they're solved the same way. If you're looking at a graph, the graph tells you where you're above or below the x-axis and also when you're on the x-axis. So if we go back to this one right here, try not to do too much with this problem, but if I were to say, where is this function greater than or equal to 0, would you stay to the left of -3? No. Would you stay between -3 and -2? Yes. Would you go between -2 and 0? No. You would be at 0 here because you can be equal to 0. But on either side of 0, the graph is already below the x-axis. So 0 to 1, no. Once you get past 1, this graph stays above the x-axis. So from the graph, you could answer the question about inequality. So everything we did before when we were solving equations, even the linear equations, you can also solve those with the graph if you know where the x-intercepts are. The graph helps you understand the answer to the inequality. With the inequality, you have many numbers that are going to make the answer bigger than 0 or less than 0. The x-intercepts serve as a dividing line. So for polynomial functions, we spend a lot of time talking about x-intercepts and zeros. For rational functions, we talk a lot about not only the x-intercepts, but also the vertical asymptotes. Now, that being said, we like the continuous functions, right? We like those in calculus as well. This is not a continuous function. This is not a continuous function. This is not a continuous function. So we kind of have to break up our analysis here and just talk about the parts in which you can analyze the function where it actually is going to be continuous. We can talk about what's going on with this part of the graph or this part of the graph right here. We just can't do anything at 0. One of the first concepts we'll talk about in calculus is the idea of a limit. And limits need to exist if we're going to talk about analyzing these functions. All right, so we did quite a lot here on number 4, answered the question and also answered questions about the inequalities. There is another page further down here that does some more with rational function inequalities. I think it's after the page we looked at on Wednesday. So we did the polynomial one here. There's also a couple for rationals. So x minus 3 over x plus 5 is less than 0. Oh, that's the only one. Okay. So you can take a look at that one too if you want to practice that technique. I don't think it's going to take us a long time to get through this section here, section 3.8. It's mostly reviewing the definition of a one-to-one function, idea of an inverse. But if you look at the objectives here, it's really focusing on polynomial functions and saying which one of those are invertible and which ones are not. Well, if you remember our toolkit functions, only 2 of these are invertible. X cubed. Why is an x squared invertible? Doesn't pass the horizontal line test. It is not a one-to-one function. Now, that being said, most third-degree polynomials are not one-to-one functions either, because if you take x cubed minus x, you know what that graph looks like? It goes up, it goes down. It has a couple of x-intercepts. So that graph does not satisfy the horizontal line test either. So x cubed, yeah, that one works because it doesn't have any places where the graph turns around like a parabola does. But most third-degree polynomials, as we've seen, are not like that. X to the 4th, ouch. Odd powers could be 1-to-1. For those who did technology project number 1, you had a graph, I think it was a 7th or a 9th degree polynomial. It actually on your calculator or decimals turned out to look like this. So that one was 1-to-1. But then there was another one, which was a different power, odd power, that had a couple of turning points. So that one was no longer 1-to-1. So we can still do this analysis with the inverses, as long as you restrict the function so you can talk about it being 1-to-1. X minus 6 squared is a parabola. It looks like this. When you look at the graph, you say that's definitely not a 1-to-1 function. But if you were to restrict the domain, so for those who did technology product number 1, Torricelli's law, you only looked at the function on a given interval where the function was 1-to-1. Same thing's happening here. So if you restrict the domain, you could use either one of these two restrictions and say, now we can talk about inverse. Bigger than 6, less than 6. So if I erase half of the parabola, I don't know if this is going to erase half or not. Yes, that's a 1-to-1 function. So we can do the inverse. Or you might have a reason to restrict it so that you get rid of that part. So once it's a 1-to-1 function, you can still analyze it the same way as before. Get the graph, switch your x's and your y's, f of g of x is equal to g of f of x, which is equal to x. So this is a property we're going to be using quite a bit. It's showing that one function undoes the other. So if two functions are going to be inverses, both these are true. And there's one other type of problem you want to be ready for, and that would be, that's a slightly different calculation here. If I can find one of these. Yeah. If you had to come up with an inverse formula for this one, x over x minus 2, when you switch x and y, you have two spots where there is y, and you have to solve y. So how do you solve that equation for y? You got to do a little bit more in terms of solving for y. But if it's 1-to-1, you can do it. Some rational functions are not 1-to-1. If we go back to the ones we took a look at here. I'm sorry, I keep jumping back and forth here. Is this a 1-to-1 function? Nope. Are any of these graphs 1-to-1? Nope. Do you think the graph of, yeah, that one is 1-to-1? That one is. I almost shook my head on that one. But it's not usual that a rational function is going to be 1-to-1. But if it is, you can find inverse. If it isn't, you can restrict it and say, stay to the left of a given number or to the right of a given number, either way. So that's kind of the focus of section 3. We'll do a little bit more with that on Monday, but you should have enough to at least get the online homework started for that section. All right, I will post the solutions to what we're doing in class on the chapter 3 examples key, and then also the tape of this as well once it's all uploaded. Any other questions for now? Technology project number 2 is due on Monday. So if you have any questions, you can send me a message over the weekend. I'll get everything back to you for those who handed stuff in on Monday. I'll give you a doggy update Monday. It's good news. And I'm hoping we'll be able to meet 3 times in person next week. There's a first time for everything, right? So have a good weekend, everybody. I will see you on Monday.
Have a good day.
Yep.